Hello everyone, welcome in a new video. In this video, we are going to understand about the new scheduling algorithm which is called round robin scheduling algorithm. Okay, this scheduling algorithm is basically different from the other scheduling algorithm what we studied in our previous videos. Why I say this? Because this scheduling algorithm basically used in a real life. Okay, this is a practical scheduling algorithm, not like the others, because we whatever the scheduling algorithm we discuss, all the scheduling algorithms are non-practical. Okay, just a theoretical. This scheduling algorithm is a practical. So let's start that what is a round robin, how we solve the question in this. So first of all, we have to understand about the scheduling criteria. So for selecting a process in a round robin scheduling algorithm, we need two things. First one is called arrival time, AT, which is arrival time, and the second important thing is called a quantum, or you can say time quantum. These okay, so these two things is necessary to solve a question uh, in a round robin scheduling algorithm. Now we know about the arrival time, that basically the process arrive in a ready queue, so that time is called arrival time. So we know that what is the arrival time. What is the new things? Time quantum. So when you are solving this particular question, it is given in a question as well that time quantum is like 2, time quantum is like 3. So whatever the time quantum is, it is given in a question. Okay, so we have to execute the process according to the time quantum. If it says 2, it means we have to execute a process 2 unit time. If the time quantum is 3, then we have to provide CPU to a process for a 3 unit of time. Okay, so whatever the time quantum is, we have to assign CPU up to that amount of time only. Okay, so this is what our scheduling criteria. And if there is a tie, if tie because here the time quantum is basically the same for all the processes, so there is a tie between an arrival time. If a two processes occur at a 0 0 arrival time, or 1 1 arrival time, or let's say three processes come at 2 2 2 arrival time. So if this thing happen, if there is a tie in an arrival time, then what we have to do is we have to follow a FCFS rule. What says FCFS? Let's say P1 P2 is the two processes that come at a 0 0 arrival time. So what FCFS do, those process who come first will get a CPU first. So we see why IDs of a process. So ID of this process is what 1, ID of the other process is what 2. So 1 is less than 2. So we assume that P1 come first and P2 come second. So this thing happen in this if there is a tie between an arrival times. Okay. This is a scheduling criteria. Now the next thing is what a type of a process is. So type of algorithm. So which type of algorithm it is? It is a preemptive type of algorithm. It is a preemptive type of algorithm. What is the meaning of a preemptive? Preemptive means whenever process run, operating system have a power to snatch CPU from a running process. Why? Because some other highly prioritized process come and that process need a CPU. So operating system what do? Operating system snatch the CPU from a current running process. So this thing happen. So this is what a preemptive thing is. Okay. So and this scheduling algorithm is a preemptive type of algorithm. Now, if you want to define a quantum, if you want to define a quantum, or sometimes the quantum is also known as a time slice. Time slice. Okay, both are same, both basically the same. Time quantum or a time slice. Now if you want to define it, you can define it like the maximum amount of time of which process run on a CPU, because if the time quantum is 2, so maximum process can execute 2. If a time quantum is 5, then the maximum time process can spend on a CPU is what? 5. I said maximum time. If the burst time of a particular process is 3, so definitely it is spent 3 unit of a time in a CPU. Okay, so the maximum amount of time is spent on a process or on basically on CPU is basically a time quantum, or you can say time slice. Okay, so maximum amount of time of which a process runs on a CPU at a time. This is what a time quantum. That's called a time quantum. So I hope you understand about the scheduling guide, the types of algorithm, which type of algorithm it is, and what is the time quantum. Now let's solve a question. So we have a processes. We have now uh, four processes: P1, P2, P3, and P4. Four processes are available. Arrival time of all the processes are same, 0, 0, 0, 0, and the burst time for the process is like 3, 6, 4, and 5. So here you can see that, or what you observe is that the arrival time is same. So if there is a tie between an arrival times, then what we have to do is we have to select that a process according to their ID. So one is basically smaller than all the other IDs. So P1 is come first, then P2, then P3, then P4. So we have to select the process in this way. And we know that this is basically a preemptive type of process. So any process which is a preemptive type, then we have to make a new section which is called a burst type. Why I say this? So that we can write the changes accordingly, because now it's a preemptive type of a process. So there is a switching between the process there. So if there is a switching between the process, it means what? It means they are not run completely. So what burst time left, so we have to write it in a new table. Okay, so this is how we're gonna solve this. Okay, so now what we have to do is we have to make a Gantt chart. First of all, the time quantum given for this particular question is the time quantum is 2, means the maximum time process can spend on a CPU is what? 2 unit. Now let's make a Gantt chart and try to solve this. So Gantt chart. Okay, so this is a Gantt chart. Okay, initially process is 0. Okay, initial the time is what? 0. After that, okay, so is at 0, how many processes are available? All the processes are available to execute. P1, P2, P3, P4, all the processes are available to execute. If all the processes are available to execute, then we have to select process according to FCF. So P1 have a chance to get a CPU first. P1. How much time P1 spend on a CPU? Only 2 quantum unit. Only 2 unit. Why I say this? Because the time quantum is what? 2. Maximum time. Okay. Maximum time a process can spend on a CPU is what? 2. Okay. Maximum time process can spend on a CPU is 2. So the P1 process spend time on a CPU is what? 2. Okay. So from 0 to, after that, the burst time left for this process is what? 1 only. Okay, so because 2 is run, this process run 2 unit of time, so the time left, the burst time left is what? 1. Now after 2 we have all these processes available. We have all the processes available, but we are going to select P2 process. We are going to select P2 process. Okay, how we are selecting this process in this case? For that, what you have to do is you have to make a ready queue. One thing you have to do is, in this type of a question, you have to make a ready queue. What is a ready queue? Ready queue basically define the sequences of the process. Okay, which process come after a running process. For example, here there is a tie between all the arrival times. So all the processes are available. So we write all the process in a sequence. So P1 come first according to FCFS, then P2, then P3, then P4. Okay, so in this way the processes are available to execute. Okay, so P1 execute first, so remove P1 from a ready queue and put it in a Gantt chart or put it in a running queue. P1 execute from 0 to 2. After P1, the next process which is available to execute is what? P2. Okay, so because after P1, what's the other process in a ready queue? P2. So P2 is used, P2 is the next process which is basically start running. So P2 is run only 2 to 4. Why I say that 2 to 4? Because the time quantum is what? 2. So every process run only 2 unit of a time. So from 6 to 4, the burst time left for the P2 process is what? 4. The one thing that you also have to do is what? P1 is completed. First of all, P1 is complete. there is a burst time left in a P1? So the answer is yes. If yes, then what we have to do is we have to add this process at last in a ready queue. Similar with P2. Some burst time is left. Yes, left. So we have to add P2 as well. So we have to add P2 here. We have to write all the processes till the processes are not completely executed. So P2 is run. After that, the other process what P3. So P3 from 4 to 6, only 2 quantum. Every process can able to run maximum 2 unit of a time. So the time left for the P3 is what? 2. And P3 bus time is what? Left. So we have to add P3 in a ready queue as well. After P3, P4 process get a CPU. So the time become 8 because every process can run only 2 unit of a time. So the P4 only run 2. So the time left, the bus time left for the P2 is what? 3. P4 is what? 3. And P4 are left. So P4 is also added in a queue, in a ready queue. After P4, the next process is what? P1. So P1 remove from a ready queue, add in a running queue. So from 8 to 10, why I write 8 to 10? Because every process can able to run uh, only a 2 unit of a time. But if you write like this, so you will make a mistake. Why I see this? You will make a mistake because the burst time left for the P1 process is what? 1. The burst time left for the P1 process is what? 1, and you execute 2. So definitely this thing is not possible if the time is the process need only 1 unit of time. How you can spend 2 unit, how that process spend 2 unit of a time in a CPU? So it cannot. So it run only 1 unit of a time. Time quantum doesn't mean that you have to execute process till that time. That time quantum is basically a maximum amount of a time that process is spent on a CPU. Minimum it can spend minimum that a time quantum. Okay. So P1 remove and P1 is completed. So no need to add P1 in a ready queue because P1 is completed. After that, after P1, the other process is what? P2, remove P2 from a ready queue, add in this Gantt chart. So from 10 to 11, 2 quantum unit because it can spend time which is 2. So the time left, the bus time left for the P2 is what? 2. There is bus time left. So yes, answer is yes. So we have to add P2 as well in a ready queue. After P2, P3 processes are available. So P3, the P3, so P3 can able to execute maximum 2 unit of time in a CPU, and its bus time is also 2, so it can completely execute. So from 11 to 13 it can completely execute. P3 is also completed. After that, P4 in a ready queue, so P4 get a CPU from 13 to 15 because it can able to execute 2 unit of a time. So that bus time left for the P4 is what? 1. Bus time left, so we have to add P4 in a ready queue as well. After that, P2 is a process. Remove from a ready queue, add in a Gantt chart or in a running queue. P4, then P2 from 15 to 2 unit of a time. So it completely execute 15 to 17. After that, P4, one process left, P4, and the burst time is what? 1. So P4 get a CPU and the completion time become 18. So this is how you have to make a Gantt chart. The Gantt chart we make is correct or not. How we determine what is the completion time of a last process, which is 18. If you sum all the burst time, if you will get 18, it means your Gantt chart is correct. So 18 and the burst time is 3, 6, 4, 6 and 4, 10, 5, 15 and 3, 18. Yes, our Gantt chart is correct. Okay. So now you can easily find out the average of turnaround time, average of waiting time. Okay, you know that how we can find out these things. What you have to do is write a completion time minus arrival time from a completion time, you will get turnaround time. Okay, so I write completion time for this process is basically for the P1, P2, P3 and P4. Okay, so for P1 the completion time is what? 9. For the P2 completion time is 17, P3 the completion time is 13 and the P4 completion time is 18. So if what is a turnaround time? Completion time minus arrival time, you will subtract it, you will get TAT. And what is the waiting time? Turnaround time minus burst time, you will get a waiting time. So if you sum all TAT divided by the number of process, you will get average turnaround time. So for this average turnaround time is what all the things all the TAT you will find, which is what 9, 17, 13, 18. Why? Because arrival time for all the process is 0. So 9 minus 0, 17 minus 0, 13 minus 0, 18 minus 0 is like this. If you add all these things, whatever you get divided by the 4. Why 4? Because 4 processes are available, P1, P2, P3 and P4. Similar thing you have to do with the waiting time. So the average waiting time for this process is whatever the values is, sum up all the values divided by 4 divided by the number of process, you will get average waiting time. Comment down your answer. Okay, so this is how you have to solve a round robin scheduling algorithm questions. Okay, now if a question asks like how many context switching is there in this Gantt chart, in this process, in this question, how many context switching is there? So what's your answer? Your answer should or your answer is like 9. Your answer is basically 9. Why I 9? Count that from P1 to P2 one context switch, P2 to P3 2, 3, 4, 5, 6, 7, 8 and the 9. Okay, so how many context switching is there? There is context switching, there is a 9 context switching in this particular question. Okay, so this type of question is asked in a gate exam and your college point of view. Okay, you have to give what is average TAT, what is average waiting time, what is a context switching, and it can say that if there is a context switch from P1 to P2, so true or false in this way as well the question asked in a gate examination. So if this is that there is a context switching between P1 to P2, so the answer is yes. Here you can see that P1 is there, P2 is there, so it basically continuously it in a Gantt chart, so it means context switching between P1 to P2 is there. But a question says that P1 to P3 is there is a context switching between P1 and P3, so the answer should be no. P1 to P3 there is no context switching. Okay, P1 to P2, P2 to P3 there is a context switching, but P1 to P3 no. So this type of a question is asked in a gate exam. Okay, so now let's solve one more question of the round robin scheduling algorithm. Processes we have is P1, P2, P3, P4, P5, P6. So we have 6 processes available and arrival time is like 0, 1, 2, 3, 4 and 5. So this is what arrival time, and burst time is like 6, 5, 5, 4, 3, 2, 4. What you have to do is you have to find out the average TAT and average waiting time. So how you can do that? This is a non-preemptive process. So what you have to do is you have to make a separate column for the burst time calculation. So 6, 5, 4, 3, 2, 4. Okay. So now what you have to do is you have to first of all make a Gantt chart. So Gantt chart is, this is the Gantt chart. Okay. Wait a minute. So first of all, what we have to do is we have to make a Gantt chart to write down which process is basically there. And one more thing we needed is which is a ready queue, because without ready queue you cannot know that which process come next. Okay, so ready queue is also important. This is what a ready queue, and this is what a Gantt chart. Okay, so these two things is necessary to solve question. So at 0, how many processes are available? One process available, P1. So P1 go in a ready queue. So P1 is available. So P1 come in a running queue or in a Gantt chart. Okay, so the main thing is time quantum. So the time quantum for this particular question is also 2. Now you have to solve. Pause the video and try to solve by yourself. Try to make a Gantt chart by yourself. And if you are not able to do that, then resume the video. Okay. So P1 is a process who come first. So P1 get a CPU. So it run only 2. So the burst time left is what 4. Okay. So at 2, now this is a very important thing. Now you can see that the arrival time is 2. How many processes are available? P1 is also available because it's not completely executed. So P1 is here. P2 is there and P3 is there. Okay, all these are now in this case three processes there. Now how you can assign these process? First of all, you have to assign this process according to the arrival time. So among P2 and P3, now you cannot select P1 if because bus time is left, so you have to run. So if you write like this P1 then again P1, then it's basically you are running only one process at a time. Okay, so it's similar to like FCFS. It's similar to some scheduling algorithm we discussed. Okay, so this thing is not going to happen in round robin. What you have to do is at 0 to 1, because P1 is execute from 0 to 1, then 1 to 2. Again, this way the P1 is basically run. And at 2, P1 leave the CPU. So till 2, two more processes are available, P2 and P3. So first of all, we have to add P2 and P3 in a red queue according to the arrival time. So P1, P2 come first. So P2 will get come first in a red queue, and then P3 comes, so P3 will get in a red queue. After that, because P1 is left, P1 is not completely executed, so P1 is come after the adding of these processes. This is an important thing you have to basically remember. This is a very important thing. First of all, you have to add the process who come at this arrival time, then you have to add that process you run if there is a bus time left. Okay, now P1 is completed. After that, P2 will get a CPU from 2 to 4 because time quantum is 2, so maximum it can execute only 2. So time left for the P2 is what? 3. Now at a 4 arrival time, how many processes are available? P4 and P5 processes is also available. So what you have to do, you have to add first of all these processes, and if there is a bus time left for the P2, then you add P2. So P4 and P5, P3, P4 come first, arrival time is got 3, and then P5. So first of all, you have to add P4 and you have to add P5 and you have to add P2 because bus time of P2 is left. P2 is not completely execute, so you have to add P2 in this. After P2, P3 get a CPU from 4 to 8. So the time left is what? 2. From 4 to 8, now the last process is also available, P6 is also available. So P6, and then there is a bus time left for the current process for the P3. Yes, bus time left, so you have to add P3 as well. After P3, P1 process get a CPU. Okay, so here you can see that it solve one basic problem, that P1 having a very highest bus time, then also he will get CPU. Okay, so we can conclude with this thing is that there is no starvation problem in this scheduling algorithm. Okay, because starvation is what, when the small process have to wait for a long amount of time. Here small process is also there. Conway effect is also not there in this scheduling algorithm. Conway effect is what, first big process get a CPU and a small process does not get a CPU for a predefined amount of a time, for an indefinite amount of a time. So these problems basically solve in this round robin scheduling algorithm we observe here. After that, okay, so P1 from 8 to 10, so the burst time left is what? 2. Okay, so and P1 is basically P1 burst time is left, P1 is not completely executed, so P2 you have to add P2. Why I directly add P2? Because now no more processes are available, so that we can add in a ready queue. So only that one process is available, which is P1, so we have to add P1. Okay, so not P. Okay, so not P2, P1. It's a P1 process. So after that P4 get a CPU. So P4 from 10 to 12, P4 10 to 12. So the bus time left is what? 1. 10 to 12. Bus time left is what? 1. Okay. So the bus time left is what? 1, and so bus time left is from P1. The next process is what? P4. After that P5 will get a CPU. P5 the bus time is what? 2, and time quantum is also 2. So P5 is completely executed at 14. So the completion time for the P5 is what? 14. Okay, so P1 is what? 6. Okay, so we made a mistake. It is what? 6 and 8. Okay, so from 4 to 6, 6 to 8, 8 to 10, and 10 to 12. So okay, so this is how this is a mistake. Okay, So P5 is now completed, and the completion time of P5 is what, 12. After that completion of a P5, so there is no P5, so we are not going to add this process. P2, P2 will get a CPU, and the completion time become 14. P2, the bus time left is what, 1. Bus time is left, so we have to add P2 in a ready queue. After P2, P6 get a CPU, P6, so the bus time left is what, 2. Bus time left, yes, bus time left, so it will add in a ready queue as well, and the completion time becomes 16 for the P6. After that, P3, P3, so P3, the bus time left is what, 2, and a time quantum is also 2, so at 18 P3 is completed, so completion time for P3 is what, 18. Okay, then P1, the bus time left is 2 and time quantum is also 2. So at 20, P1 is also completed. So no need to add this process in a ready queue. After P1, P4 get a CPU. P4, the time left for a P4 is 1. Okay, so we have to execute only one. So 21 is the completion time for the P4. Remember this, you because so many times a student make a mistake that it write from 20 to 22, but the bus time of a P4 process is also is only 1. So CPU is on the process spend only 1 unit of a time in a CPU, and after the completion it terminate, it leave the process, other process get a CPU at that time. Okay, time quantum is a maximum time that process can spend on a CPU. Minimally it can spend according to the burst. Okay, then P2, so for the P2 the burst time left for the P2 is what, 1. So 1 left, it means what, from P4 to P2 it's only 1, so 22 is basically a okay, so 22 is basically a completion time for P2, only one process left, and P3 is completed, so no need to add P3 now. And P4 is also completed here from 20 to 21, so P4 is completed, only one process left, which is P6. So P6 will get a CPU, and the bus time for P6 is what, 2. So at 24 P6 is also completed. So this is what a Gantt chart is look like. So you have to check that the Gantt chart we make is correct or not. So you have to sum all the burst time and check the completion time for the last process. So 6 and 5, 11, 4, 11 and 4, 15, 15 and this 20, 3 and 2, 20 and 4, 24. So burst time is equal to the completion time for the last process. It means we make a correct Gantt chart. Okay, now you can easily find out the completion time, turnaround time, waiting time, and you can easily find out the average turnaround time and average waiting time. Okay, so this thing you have to done by yourself. The main thing to solve a question of a round robin is you have to make a ready queue. Without ready queue you cannot able to solve this question. Okay, so this is how you have to solve. And if a question asks what now, the number of context switching in this case, number of context switches. So what you said, how many number of context switching is there? So you have to count from P1 to P2, 1, P2 to P3, P3 to P1, P4, P5, P2, P6, 3, 1, 4, 2 and 6. So there are 12 context switching is there. So the answer is 12. Okay. So this is how you have to solve this question. Okay. So this is on an average, this is how the question is appear in a GATE exam. Or okay, so in this way the question is basically appear. Now if you want to solve one more question, you can do that as well. So I give you a question, the process is like P1, P2, P3, P4, P5 and P6. The arrival time for these processes are like 5, 8, 3, 6, 2 and 4, and the bus time is looking like 6, 7, 8, 3, 2, 4. Okay, so this is what a bus time. So this is the time quantum for this is what, 3, and you have to do it by yourself. Okay, so I made a Gantt chart, comment down your average TAT and average waiting time. Okay, so we solve one more question and then we moving towards the advantage and disadvantage of this particular scheduling algorithm. Okay, this much question is sufficient to understand the concept, and you have to solve more question to make a good good on this type of a question, to make yourself good in this type of a question. So 6, 7, 8, 3, 2 and 4. Gantt chart. First of all, what we have to make? Two things, ready queue and a Gantt chart. Okay, so ready queue. RQ means ready queue, and the next thing is what? After ready queue, the next thing is what? Oh. So the next thing is what? A Gantt chart. Okay. So these two things is needed to solve this type of a question. Gantt chart. At a 0, how many processes are available to execute? So the answer is nothing. No processes are able to execute at a 0. So 0, there is no process able to execute. Then we have to leave a CPU. Till when? Till 2. Because at 2, the one process P5 processes is available to execute. So P5 come in a ready. Remember this thing, what the most of the student do mistake in this here as well, that the time quantum is 3. So what do is they make idle CPU from 0 to 3. You cannot do that. Time quantum is basically the maximum time, and if there is no process in a queue, so how you can assign, how you can make idle? If a process come at early, then you have to give CPU to that process. You cannot wait, you cannot give waiting to that particular process, although there is one process in a CPU and you wait. Why? Because the time quantum is 3. So no, you cannot do that thing. You have to choose process accordingly. You have to make a ideal situation accordingly. Time quantum is basically a maximum time, not a minimum. Okay, so from 0 to 2 process, the CPU become idle, and at 2 one process come in a ready queue, which is P5. So P5 will get a CPU from 2 to 2 to 2 to 4. The burst time for the P5. Why I write 2? Why I write 4? Quantum is 3. So if you add 3 into, you will get 5. But why I write 4? Because the burst time is only 2. Time quantum is basically a maximum time process spent. Okay. So P5 is completed in one go. After that, the now arrival time is what? 4. So P5 is completed. Now the processes in a queue is what? P3 and P6. So we have to choose process according to their arrival time. P3 come first and then P6. Okay. So P5 is completed. P3 and then P6. P5 is completed, so no need to add P5. After that, P3 will get a CPU and the P3 burst time is what? 8. So it can easily spend the maximum amount of time in a CPU, which is 3. So 4 and 3 becomes 7, and burst time left for this is what? 8 minus 3, which is 5. Okay. After that, burst time after 5, now the arrival time is what? 7. Arrival time is what? 7. Some processes are available, so you have to check that. Okay, so that's now arrival time is 7. So P4 process is available, P1 process is available, 2 more processes is available. So we have to add that process in a ready queue first of all according to the arrival time. So P1 come first because the arrival time is what? 5. After that, P4 arrival time is what? 6. P8 is not added, and now we have to check that P3 bus time is left or not. So P3 bus time is left. 5 means P3 bus time is left. So we have to add P3. In this way, you have to add the process. P6 get a CPU, and the bus time is what? 4. So it can spend maximum time. The time left is what? 1. So 7 to 10. And now we have to check that at 10 some processes are able to execute or not. P2 is left. Now P2 is able to add in a queue. So P2. After that, we have to check that with the process we just run is left some bus time or not. So yes, it left some bus time. So P6 is also added in a ready queue. After P6, P1 get a CPU. After P6, P1 get a CPU. So what's the burst time of P1 is what? 6. So if it can spend maximum time, so the time left is what? 3. 10 to 13 it can spend. Add 13. Now you can see that no more processes are able to add in a queue. So you have to check that process you just run. P1 some burst time left. So the answer is yes, some burst time left. So you have to add P1 after that. Okay. After P1, P4 processes are in a ready queue. So P4 get a CPU. From now we have to check what's the burst time of a P4? 3. So it can completely execute from 13 to 16. It can execute, and P4 is now completely execute. Okay, no burst time left, so no need to add in a ready queue. After that, P3 Now the burst time left for the P3 is what, 5, so it can spend maximum time. So the time left is what, 2, 16 to 90. The burst time left, so the answer is yes. So you have to add P3. After that, P2 get a CPU. Now we have to check the burst time for the P2, which is what, 7. So you have to subtract, or you will get 4. You will get, so the burst time left for the P2 process is what, 4. 19 to 22. 19 to 22. Is burst time left for this process? Yes. So we have to add P2 in a ready queue. After that, P6. What's the burst time of P6? 1. So it cannot spend maximum time. It cannot spend only 1 unit of a time. So 22 to 23. P6 is also completed. So no need to add in a ready queue. After that, P1. What's the burst time? 3. So it can spend maximum time and it successfully completed. So 23 to 26, P1 is completed. No need to add in a ready queue. After that, P3. Burst time left for the P3 is what, 2. So it can spend only 2 from 26 to 28. Okay, only 2 unit of a time. And now P3 is also completed. So no need to add P3 in a ready queue. After that, P2 left. P2 get a CPU. What's the burst time left? Burst time is what, 4. So this is what a main point as well in this question, that what you do if you write it like 24 to 32, because only P2 process is left. So if you write like this, so this is a mistake. You made a mistake, that the time quantum is what, 3, and you write 28 to 32 means 4 unit of time you spend on a CPU. P2 spend 4 unit of time in a CPU, but the time quantum is 3. So how this possible? This thing cannot be possible. What you have to do is you have to execute P2 only 3 unit of a time from 28 to 29, 30 and 31. After that, P2 again get a CPU, so you have to make like this from 31 to 32. If you are not make like this, so you are making a mistake while calculating a context switching, because if you 28 to 32, if you write directly, so it means you are, you are decreasing one context switching. Okay, so this thing is possible, so you have to make your mind open while solving this type of a question. So now you can find average TAT and average waiting time very easily. And one more thing, that Gantt chart always start from a 0. So if the no process are available, then at that time the CPU become idle. So if a question asks the number of context switching, so how many context switching is there from P2, P5 to P3? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Number of context switching is 11. So 11 context switching is there. Okay, so this is how you have to solve this question. Okay, now we solve a lot of question. Now you have to practice a lot of question. Okay, now we are moving towards the advantages and the disadvantage of this scheduling algorithm. First of all, we talk about the advantage, that what is the advantage of this scheduling algorithm. So the advantage is that all processes are executed one by one. There is no starvation problem in this case, because every small big bus time process are able to execute. Okay, and the next thing is what, every process get a chance. Okay, so every process is get a chance. So this is what one advantage, that all processes are executed one by one. All processes are executed one by one. All processes are executed one by one. So no starvation is there. So no starvation is there. So no starvation is there. Or what is the next thing? Next thing is what, it's better interactivity or better interactiveness. Better interactiveness. What does this mean? Here you can see that P5 to P3, P3 to P6. So there is a context switching, there is an interaction between a CPU again and again and again. Okay, because in sometime what happen is, when a big process get a CPU, it will execute completely. So small process or other process will not get a chance. So this thing is not happen. One process run, one process run, one process run, one process run. So better interactivity with the CPU, and one by one all the processes are executed. Third is what, burst time is not required to be known in this advance. Burst time is not required to known in advance. What does this mean? This is what a disadvantage in the scheduling algorithms. In a previous scheduling algorithm, what we discussed, that burst time is not known, so there is no practical implementation. In this scheduling algorithm, burst time, we doesn't need to know about the burst time because we know about the time quantum. So whatever the burst time is, the process can spend only this amount, this time quantum, this quantum of time the process can spend on a CPU, not more than that. Okay, so there is a no need to require a burst time in advance. That's why it's very helpful in a practical implementation as well. So this is what an advantage is. Okay, now talk about the disadvantage. Okay, so disadvantage is that, first of all, that it's whatever the average waiting time and average turnaround time of you calculate by round robin scheduling algorithm is more, DT are more. Okay, if you compare with SRTF, SJF, or whatever scheduling algorithm, if you compare, your the round robin scheduling algorithm will give you more average turnaround time and average waiting time. Okay, so this is what a disadvantage. And the second disadvantage is it cannot degrade to FCFS. It can degrade. It can degrade to FCFS. It can behave like FCFS. Okay. So this is what the disadvantage and advantages of round robin scheduling algorithm. I hope you understand that how we solve round robin scheduling algorithm. Comment down the results of these question. Okay, 1, 2, 3, three question. Three. You have to comment down the 6 values. Okay. So this is round robin scheduling algorithm. Thank you for watching this video. Like the video and subscribe my channel.